Okay, scholars, so we are almost done with our unit on rotation, and I wanted to I'll just give you a little glimpse ahead. We still need to talk about two main topics. First of all, what we're going to discuss today, angular momentum. Remember, we've said already that all this rotation stuff is just going to map onto the rest of the course that we've had before. We've had kinematics, we've had forces, we've had energy, and we've had momentum. We've talked about everything in that way except for momentum so far. So we do need to discuss rotational or angular momentum. That's what we're going to discuss today. And then after that, we need to have a special conversation about equilibrium. So far, you guys understand that equilibrium deals with Newton's forces, with forces and Newton's laws. You know that something is in equilibrium when the forces in the x and y directions are equal to 0. There's no net force. Well, we need to expand this and think about the idea that there's another requirement for equilibrium, and that is for the net torque to be 0. And we're just going to have a very brief discussion about that to finish out the unit. But for today, let's talk about angular momentum. So first we may want to remind ourselves what momentum is at all. So remember that translational momentum was a vector whose symbol was p, and it was very simply the product of an object's mass times its velocity. Momentum can be thought of as like the quantity of motion that an object has. And remember that we discussed how momentum is conserved when there are no external forces acting on your system. And it allowed us to analyze interactions of particles when there's no external force acting on the particles. So when particles are colliding, things like that, we analyze the conservation of momentum. So you know that momentum is conserved. So these are just reminders about translational momentum. We haven't gotten to angular yet. Momentum in general is conserved when the net external force on the system is equal to 0. And we said those are situations like analyzing collisions, explosions, things like that. All right. And we said that a change in momentum can be defined as an impulse. And an impulse is a force that is acting over some time period. Let's talk real quick. Let's remind ourselves where these equations come from. We know that a net force causes acceleration. We know that acceleration is the time derivative of velocity. And therefore, if the mass of our system is not changing, we can say that we can make this differential equation f dt equals mdv, where mdv would be like a small, tiny, infinitesimal change in momentum. How do we go from infinitesimal changes to big, chunky changes? We take the integral, right? So we can integrate both sides of this, and this mdv will become m delta v, which is just change in momentum. So that's how we got that equation. And again, that is defined as an impulse. All right, so a force acting over some time period causes an object to accelerate over some time period, giving it some change in velocity. So there's some reminders for you for momentum. Let's now apply all of these same ideas to angular momentum. And this is kind of weird, and it's going to be a little bit wacky to think about, but first of all, you need to understand that there are two types of angular momentum. And I really don't like to use that word type, but I don't know another way of talking about it. There are like two perspectives, two scenarios, two aspects, I suppose we could say, that go into angular momentum. So let's talk about those two now. The first type, so to speak, of angular momentum is what I'm going to refer to as translational angular momentum. Now, this seems like a contradiction in terms. How can we have a translational angular quantity? Um, and haven't we already talked about translational momentum right up here? Isn't this the expression for the momentum of an object that's moving translationally with a translational velocity? Yes, that's true, and yes, we still need this, but there is a second type of momentum known as angular momentum. And an object is said to have angular momentum when it is moving. So we have like an object or a rigid body that is moving translationally relative to some point, where that point is functioning as an axis of rotation. So to help you understand why we talk about translational angular momentum, we can just look at a wheel. Let's look at a wheel that's spinning. Here's the axis of rotation of the wheel. Here's a point particle on the wheel. If I look at just that single point particle, let's say my wheel is spinning in the positive direction, so counterclockwise, you guys know that this point right here has an instantaneous tangential velocity just like that. So really what we're saying is that this point particle here, at every instant, it has nothing but tangential velocities, and therefore at every instant it has nothing but translational motion. It's just that it has, instantaneous translational motion that's changing direction to make a circular path. This point on this wheel and the wheel as a whole is truly rotating. We do have to talk about it in terms of angular quantities, but if we just look at one single point on the wheel, there's no way that we could talk about it rotating or it moving angularly. Does that make sense? If we just zoom in and focus on this single point, there is no way for us to talk about the fact that it's rotating. It's just translating. However, it's part of this rotating angular system. So the concept of translational angular momentum is motivated by this idea that objects that are rotating, if we zoom in and focus on a single point particle, that point particle cannot be said to be rotating. It just has translational velocity and therefore translational momentum. However, it is part of this larger picture and pattern of the large object rotating. So here's the equation for this type of angular momentum. First of all, L is the letter that we give to angular momentum. And for this definition, we're going to use this equation, R cross P. It is another cross product, a vector product of, once again, our R vector, and then you guys know this as regular translational momentum. So this just allows us to kind of translate translational momentum into angular momentum, where this equation, you guys need to know, applies for this scenario, an object moving translationally relative to some point or some axis of rotation. So we use this perspective when we're worried about an object or a point particle that's moving, but we're not worried about its pure rotation yet. So maybe we could say this, we're not yet not concerned here with, we may just be worried about what a single point on that object is doing, or what a point in space is doing, how it's moving translationally. So here's kind of the wacky thing. Every object in space that's moving through space, every point particle moving through space, even if that object is not rotating, has both regular old momentum, plain old momentum that we have discussed previously, and any point particle or object moving, just if it's moving in a straight line through space, it also has this angular momentum. It has a translational angular momentum. We'll talk a little bit more about why that's the case later. It's much more evident, makes much more sense when we're looking at a point particle that is part of a system that is actually rotating. Okay, enough about that. Let's talk about the equation. So angular momentum is given by L. It's a cross product. You guys should be familiar with cross products by now. You know what this R vector is. That R vector is drawn from the axis of rotation out to the point that we are interested in. So here's my R vector. And the momentum vector will always be pointing in the same direction that the velocity vector is, won't it? Because that's where momentum gets its direction from, is from the direction of velocity. So here's my velocity vector. That's also going to be the direction of my momentum vector here. So remember what the cross product is concerned with. It's concerned with the sine of the angle between the two vectors. In this example, that angle is always going to be 90 degrees. So in this specific example, in this example only, I get R times P, which is P is mv, so m times v times r. This is the simplest form of angular momentum when the velocity and therefore the momentum vector are already perpendicular to this r vector. The sine of theta is just 1, and we get this, mvr. So that is true for this example. This will be true for all examples of translational angular momentum when we're looking at a point in space. And remember the definition, that point in space is moving relative to some axis of rotation. That's where the r vector comes in, right? We're basically modifying the momentum vector by taking it into a cross product with this r vector, where that r vector tells us the distance and orientation away from some fixed point in space. This axis of rotation is a fixed point. Okay? Let's look at another example. So, as I said earlier, it's clear why we would want to call this angular momentum. This point particle, it is never truly like rotating. It's always moving translationally, but it's part of a rotational system. So this is one perspective we could take then on angular momentum. What if, though, we just have a point particle that is not part of a rotating system, and that point particle is zooming through space, and it has a velocity this way and a momentum vector therefore that way. It's got a mass of m or something, and it's moving in a straight line through space forever. Can it be said to have an angular momentum? Well, yes, it can, as long as we define some point, some fixed point in space, or some axis of rotation. In other words, let's map this bad boy onto a Cartesian plane, and let's say that here's the origin, and I can now define the angular momentum of this particle. Even though this particle is always moving in a straight line, it's just going to map out this trajectory, right? Its trajectory is going to be in a straight line forever. So even though that's the case, as long as I have some fixed point in space that is acting like a quote-unquote axis of rotation, some fixed point that I can define angular momentum of an object from, then I can say that thing has an angular momentum. So let's see what the angular momentum of this particle is. Well, first thing I'm going to have to do is identify the momentum vector, the translational momentum vector. That's here. It has this particle is moving to the left with some velocity. So let's say that's equal to just m times v, where the velocity is to the left. And I may want to call it negative because my velocity is pointing to the left. So negative mv. So there's my momentum vector, and you remember that translational angular momentum, the angular momentum for any object moving translationally through space as defined from a fixed point in space, whether an axis of rotation or just a point. I need an r vector, right? So the r vector is going to be the vector that's drawn from the axis of rotation or the fixed point up to the momentum vector, just like that. And I'm worried about the cross product of those. So here's my r vector. And the cross product, remember I'm worried about the sine of the angle between them, and you guys should be familiar with this. You can redraw these vectors tail to tail and take the angle that way, this angle here, or you don't have to do that because the sine of complementary angles is always the same. I can take just this angle here, the angle between them. This angle also shows up here in my diagram. All right, so I can say now that the angular momentum of this particle m with respect to this axis of rotation, the angular momentum is going to be equal to rp sine of theta. I know that p is negative mv, so let's say negative m vr. I like to rearrange it like that. It really doesn't matter. Times the sine of theta. And now if I knew like a coordinate point, if I knew the position of this thing, let's say it's located right now at a coordinate of a comma b or something like that, I could be even more specific, right? I have a right triangle here whose legs would be length of a and height of b. I didn't draw that quite correctly. I should be to the point particle. Length of a, height of b. And so you guys know that sine is opposite over hypotenuse. And the hypotenuse here is going to be the square root of a squared plus b squared. That's how big my hypotenuse r is. So I could replace sine theta with opposite over hypotenuse, which would be I would get that, and that might be one answer that I would want to give for the angular momentum of this point particle with respect to this axis of rotation or this fixed point in space. So that was just an example. It is weird to think about the fact that even though this point is never rotating, as long as I define some other point in space that it's moving relative to, then I can define an angular momentum, a translational angular momentum. So I would say that this moving particle has two momenta right now. It has good old-fashioned translational momentum, and it also has this angular momentum about the origin. Let's see, I'm realizing now that I could have just left the size of this r vector as r because it also shows up in my equation. I'm just playing around and showing you guys different algebraic ways we could express things. mvr times b, and I'm just saying that the sine of theta is opposite over hypotenuse. Well, the length of my hypotenuse is r, isn't it? So that equation, yeah, this is the simplest way of putting it. Negative mv b, just like that. And this is really interesting because as my particle is zooming along here at a constant velocity, there are no net external forces acting on it. So what's true about angular momentum and any momentum? If there's no external forces acting on your particle, it's conserved. So when my particle gets here and is zooming with a momentum of p, or when it gets here and it's zooming with a momentum of p, you know, whatever I calculate its angular momentum as, I should always get this result. And you can see there that this result tells me that the angular momentum just ends up depending on how high above this axis it is. And we're going to get that same result. If my point particle is right here, for example, then my r vector would look like this. And those vectors would be perpendicular to each other already. So the sine of that angle would be, the sine of 90 would be 1. My angular momentum there would just be, therefore, would be negative mvb. I would get the exact same result because the distance here, this new r vector in my new calculation of right here, so let's say this is my first calculation, this is my second one, for when the particle has reached position 2, it's still, the same distance b away from this particle, just or from this axis of rotation. The height above the x-axis is b. So no matter where we do our calculation, we're going to get the same result because angular momentum here in this example is conserved. Okay, so I kind of got off on a little tangent there going through that example, but I'm just wanting you guys to get the hang of this idea that angular momentum, it holds for particles moving translationally, in which case we are speaking about quote-unquote translational angular momentum, and that is just when a particle has momentum relative to some point in space. That point in space could be an axis of rotation if my point is actually part of a rotating system, or it could just be a random point in space. If my moving object here, my mass, is just moving translationally and it's never rotating at all, I can still say it has an angular momentum relative to some point, and I would just need to define that point, and here I've said that point is the origin. So hopefully you guys are getting the hang of this idea of translational angular momentum. How do you think we find the direction of angular momentum? It is a vector. It's the result of a cross product, so of course we're going to use the right-hand rule. So in this example here, r cross p, I take the fingers of my right hand, match them up with my vector r, so my fingers are pointing up towards the top of my computer screen and my palm is facing to my left. I'm going to wrap my fingers around to the left because that is in the direction of my second vector, the momentum vector here. And that makes my thumb pointing toward me out of the screen. So we would say that the L vector here is facing out of the screen. In other words, we say out of the screen is positive, right? And that makes sense because this thing is moving counterclockwise, and we always consider for angular quantities counterclockwise to be positive. So don't forget about your right-hand rule for the directionality there. Yeah, so please remember that any object, even if it's just moving in a straight line, has this type of angular momentum that we refer to as translational angular momentum. All right. So that is our first type of angular momentum, translational. That is for a point particle where we're not really worried about the fact that it's rotating. It may not even be rotating. It's just moving translationally. It could just be instantaneous translational motion, but it's moving instantaneously, translationally, relative to some fixed point in space. All right. So our first type of angular momentum was translational, governed by this equation. And our next type is rotational. And in rotational angular momentum, we are concerned with the angular momentum that arises due to the rotational motion of extended bodies. So last time we talked about translational angular momentum, I used the example of a wheel that's rotating, and we said that that this point on this wheel has a translational momentum, and we could draw an r vector there and define the translational angular momentum of that point on the wheel. For rotational angular momentum, we are taking a more zoomed out perspective, looking at the wheel as a whole, looking at the extended body of the wheel, not just a point on the wheel, but the wheel as a whole. And the wheel as a whole, as it rotates, this version of angular momentum, the equation is much simpler. It is I times omega. This should look really familiar to you. This is the exact rotational equivalent of regular old momentum. Plain old momentum is this, P equals mv. These are just the direct rotational analogs. The rotational analog of m is I, rotational inertia. The rotational analog of translational velocity is omega, rotational velocity, right? So this is the angular momentum that arises due to an object, an extended body actually rotating about some axis of rotation. All right, and this one is kind of easier to calculate. You just need to know the I value for your object, the angular momentum, the angular velocity for the object, and multiply them. Directionality is exactly the same. I have not emphasized this enough, but all angular quantities, their direction is always going to lie along the axis of rotation. So in this example, my wheel is rotating around this way. That's counterclockwise. I would say it has a positive omega, and that omega therefore lies along the positive axis of rotation, so it's coming out at me. Therefore, my angular momentum would be positive as well, and that vector would be coming out at me. Okay, so that's where the direction comes from there. So to kind of help you understand these two different types of angular momentum, we can talk about the planet Earth really simply. The planet Earth has both of these, right? It has both types of angular momentum at the same time. So we could say, therefore, that the total angular momentum of the Earth as it moves around the sun is going to be equal to its angular momentum rotationally, because the Earth is rotating about its own axis. That's what gets us a day, right? And then the angular momentum that it has translationally, as it moves, the Earth itself moves through space about a fixed point, the sun, basically. So here's the sun. The big yellow one is the sun, and here's the Earth. This is a top-down view, I guess. And the Earth, as it moves around the sun, is doing two things, right? It itself is rotating. It's spinning. So that would get me this. I would have to do a calculation for the I value of the Earth. The Earth is a sphere. Spheres have an I of 2/5 mr squared times the angular velocity of the Earth, which we could actually figure out just knowing that a day is 24 hours long. And then translationally, I know that the Earth is moving in a big old circle, or an ellipse rather, around the sun, and that every given point in time it has a linear momentum that is tangent to that path, because it has a velocity tangent to that path instantaneously. And that would be r cross p, where the r vector is going to be right here. Just draw a line from the axis of rotation to the Earth. That's going to be the distance that the Earth is from the sun. The cross product with p, that's worried about the angle between those two vectors. That's a 90-degree angle. The sine of the angle is a 1. So ultimately then this is going to become mvr, where v is the tangential velocity of the Earth. And I could figure that out by knowing that the Earth rotates around the sun every 365.25 days. So the Earth has both of these types of angular momentum, Therefore, its total angular momentum would have to be the sum of them. This is worried about the fact that the Earth is spinning as it goes around the sun. It is actually rotating on its own axis. And this is worried about the fact that as it does so, it is moving like a point particle relative to a fixed point in space. So every point of the way, it has this translational angular momentum quantity, which is governed by this equation. So hopefully that kind of helps you understand the differences in the two types and how we need both of them. I'm going to try to help you appreciate the fact that these two types of angular momentum have a deep relationship. And they're not always translatable between the two. Like, for example, the Earth moving around the sun, the Earth rotates about its axis with some omega, and as it moves around the sun, it travels with some momentum like that. Those two are not related to each other. Like, the Earth is not traveling, it's not rolling across a surface, so I couldn't say that its velocity is related to its omega. So I really truly do need both separate definitions to think about what the Earth is doing as it rotates, as it revolves, and as it orbits around the sun. I do need both of them. But for something that is just spinning, like a bike wheel, here's the axis of rotation. That's always the first thing we do, right, is identify the axis of rotation. Here is my momentum vector for that point. Let's say that this thing is rotating counterclockwise with some omega. Here's an r vector. And let's say that this is a hoop. It's just a simple wheel, so it has all of its mass out here. So I can treat it like this collection of infinite point particles, right? And they all are going to have these instantaneous tangential velocities and therefore instantaneous tangential momenta. And therefore, every single point particle will have its own translational angular velocity, won't it? So if I wanted to find like the total translational angular momentum that the wheel has, that would just be me adding up all of the points, right? All the infinitesimal points as they are moving relative to this. And so I would say, therefore, that the angular momentum total of this rotating wheel could be the integral of r cross p for each of these little tiny mass pieces. And I can say that each little tiny infinitesimally a small piece of this wheel has a mass of dm. So this cross product would become dm times v. That would get me the momentum vector, the tangential velocity of each little dm. And then a cross product with r, it's always going to be 90 degrees, so that's just going to be r. V and r are constant, right? As long as this thing is not speeding up or slowing down, I can pull v out. R is constant. The radius, the distance away that each little infinitesimal point is from the axis of rotation, so I can pull it out. So this equation is going to become VR times the integral of dm. What's the integral of dm? It's m, right? So I get m VR. That would be like the total translational momentum of each of the pieces as they rotate, which is what rotational angular momentum is. It is the sum, the total, the integral of all of these little mass pieces doing their tangential thing. They each have their own translational angular momentum relative to the axis of rotation. So if I sum all of those up, now I'm looking at the extended object rotating, which is what this is all about, right? And remember that v, a tangential velocity, which is what this is equal to omega r. And so this equation would collapse down into mr squared times omega. And oh my goodness, the I value for a hoop is mr squared, and there's omega. So I just wanted to show you that these two things are related to each other. The best way of talking about what this hoop is doing is to say that it is rotating. Every single infinitesimal mass piece has this translational velocity and translational tangential momentum. Therefore, the whole object is rotating. So if I want to talk about what the whole object is doing, I can just look at this for every little dm piece, integrate it, and I get this. So that's where this comes from. This is a zoomed out view. I suppose we could say that, therefore, this is the more basic definition of angular momentum. Every object moving through space has this, and then it's just that when objects are rotating in space, I can integrate all the little dm pieces and I would get this. So they're related to each other. I'm not saying that you can like substitute them. I just wanted to show you that they are deeply related to each other. For things like the Earth that are rotating and revolving, you're going to need both of them, right? Because the Earth is truly just like a single point particle revolving in a circular path with respect to the sun. So when you just have a single point particle moving through space relative to some fixed other point, you're going to have to use this, all right? If you have an object rotating, you integrate this and you get this one, the rotational. Rotational is like a zoomed out view for an extended body that is actually spinning. This is just looking at a single point particle moving relative to some point. All right, so hopefully that helps you kind of understand the two and how they are utilized and what they mean. Okay, scholars, we need to talk about the units of this angular momentum idea real quick. So, oh boy. Yeah, so based on our two definitions of angular momentum, translational, rotational, we can figure out what the unit of angular momentum must be. So we know that regular momentum has units of kilogram meters per second, right? Remember that regular momentum is mass times velocity. And this r vector, again, is a position vector, so it has a unit of length, or rather, it shares a unit with length, meters, right? So we know that this is going to end up being meters times kilogram meters per second. And of course, that resolves into kilogram meters squared per second. So we can see that that must be the unit for angular momentum. It does not have a special name. Let's see if rotational angular momentum gets us the same unit. You know that this I value, I always ends up being some k value that's equal to 1 or less times mass times a radius squared. And so the unit of that is going to be, k is unitless, mass is kilograms, and we know that radius squared is meters squared, right? So we get kilogram meters squared. And then angular velocity, what unit does that have? It has radians per second, but radians is kind of unitless. A radian is a unitless concept. So that just brings to the table per second. And of course, we can see that these are exactly the same. So angular momentum has units of kilogram meters squared per second. Of course, we could write that like this, couldn't we? Kilogram meters squared times seconds to the negative first, however you want to write it. All right, so there's your unit for angular momentum. Please don't forget it. And yeah, it has no special name, but that's it. Okay, scholars, so I thought we would start working through some examples with rotational inertia and its conservation in a system. This example just happens to have one of my favorite cursed images in all of physics over here. So here's the scenario. We have this dude, he's standing on a turntable, he's holding his dumbbells outstretched, I guess practicing his ice skating routine or something. Um, and he's rotating with some initial rotational velocity. He pulls the dumbbells inward, and we want to know what is his new angular velocity. And we want to see if his rotational kinetic energy changes, and if it does change, we want to know where did that work come from? Where did that energy come from? If his rotational energy does indeed change. So we have all this information here. Let's start trying to interpret it and see if we can use it to answer our question. So I can see that he is holding these dumbbells and they each have a mass of 5 kilograms. His wingspan, where that term wingspan just means the length measured from fingertip to fingertip with his arms outstretched, that's 2 meters. His body itself, so he's rotating about this central axis, has this rotational inertia. And that's just for his body. We have to think about the fact that that does not include these extra masses he's holding out here. So his body itself, with respect to this central axis, has a rotational inertia of 3. But these dumbbells probably add something to that because these dumbbells add extra masses that are, what is that going to be, 1 meter each away from the axis of rotation. And he's initially rotating such that he makes 1 revolution in 2 seconds. So let's try to get some information here. I know that his initial moment of inertia is going to be the moment of inertia of his body plus the moment of inertia of the dumbbells. So don't forget that whenever you have systems like this that are composed of multiple parts, dumbbell and professor, we can sum up the rotational inertias of each of them to get the rotational inertia of that whole system. So here it tells me the professor has a rotational inertia of 3 kilogram meters squared. And the dumbbells, I know that they're 5 kilograms. And I can treat them like point particles here located a meter away from the axis of rotation because his wingspan, fingertip to fingertip, is 2 meters. And his axis of rotation is going straight down his middle. So the rotational inertia of 1 dumbbell would therefore be 1 meter squared. Remember, rotational inertia is the integral of r squared dm. And it just so happens that I don't need to use the calculus definition here because I just have like a point particle away. So rotational inertia using a collection of point particles is r squared m, the sum of that, right? So here's r squared for one of them, the mass is 5. And then my r squared times m for the other one will get me that. So it looks like that initial rotational inertia is going to be 13 kilogram meters squared. All right. So first of all, I suppose that we should talk about what concept we're using to answer this question. Let's focus on this question first, his new angular velocity. I kind of got ahead of myself getting all this information down. Well, I can see that there are no external forces acting on him that would cause a rotational change. There are no torques acting. And when your net torque is 0, I know that initial angular momentum has got to equal final angular momentum. So I'm using conservation of angular momentum here. And he is an extended body rotating, so I'm going to use rotational angular momentum, where you remember that rotational angular momentum is just I omega. So what I'm ultimately going to do is say that his initial values of I omega, the product of those has got to equal simply the product of the final values, and I'm trying to find that final angular velocity. So maybe we should make a prediction. Do we think that angular velocity will go up or down? Is he going to start spinning faster or more slowly? We can see from the nice motion blur they added to the picture that he's probably going to start spinning more quickly. Why is that the case when he brings these dumbbells in towards his center? Well, think about this. It tells us that, so if we think about the change in his rotational inertia, after he brings those dumbbells in, he has more mass closer to the axis of rotation. And remember that rotational inertia is bigger when we have more mass farther away from the axis of rotation. So by bringing those dumbbells in close to his axis of rotation, he has lowered his rotational inertia. And if, according to this equation, if rotational inertia has decreased, rotational or angular velocity must have increased. I can guess that this is probably going to go up. So let's see what we can see with rotational inertia here at the end. He pulls his arm inward, bringing each hand 0.2 meters away from his central axis of rotation, and his body has this new rotational inertia. His body, the rotational inertia of his body has gone down from 3 to 2.2. That makes sense because his arms were extended, giving him more mass farther away from his axis of rotation. He brought his arms in, and now they're closer to his axis of rotation. So here is the moment of inertia of the professor. We still have those dumbbells though, and this time they are closer to the axis of rotation, aren't they? It says that each of his hands is 0.2 meters away from the axis. So r squared times m, 0.2 squared times 5 will give me the rotational inertia contribution of one dumbbell. The other one is going to be the exact same thing, 0.2 squared times 5. You do that calculation and you're going to get 2.6 kilogram meters squared. So his rotational inertia went way down compared to what it was before, so we should predict that his angular velocity will go up. So now all we need to do is figure out an expression for the initial angular velocity, and we'll be good to go with this equation. So what do I know is true beforehand? Well, it says he makes 1 revolution in 2 seconds. So 1 revolution every 2 seconds. Remember what the unit of angular velocity needs to be. It needs to be radians per second. So all I need to do is a quick unit conversion. I know that 1 revolution, 1 complete circular spin is equal to how many radians? How many radians are in your unit circle? 2 pi, right? So 2 pi rads. And radians are really, they're really unitless, but that's fine for me to write it there. So I can see that his initial rotational velocity is therefore pi radians per second. All right, just like that. And now I have everything I need to solve this problem. I can just plug and chug into this equation. I like to rearrange the equation first. So here's my conservation of angular momentum equation. I can divide both sides by IF, and I can see that my final angular momentum is going to be his initial rotational inertia times his initial angular velocity divided by final rotational inertia, just like that. So it's going to be 13 times pi divided by 2.6, some simple algebra there. And when we do that, we get 15.7 radians per second, which is of course much bigger than pi, and that's what we predicted. His initial rotational angular velocity was pi radians per second. His new one is 15.7 radians per second. What if we wanted to know how many revolutions that was per second? How many revolutions is he making every second? We know last time he was making 1 revolution every 2 seconds, or half a revolution per second. Well, I could do a quick conversion here, couldn't I? 15.7 radians every 1 second. Just convert it back. This could be something we're interested in. It's difficult for us as humans to look at something rotating and count the radians, but we can count the revolutions, can't we? So we may be interested in what we would actually see this dude doing. And I know that there are 2 pi radians in every 1 revolution. And you do that and you're going to get something close to 2.5 revolutions per second. So those are equivalent And we can see that that is definitely more than what he was doing before. And you guys have all seen this with ice skaters and things like that. They're spinning around, they bring their arms in closer, and they start to rotate more quickly. If there's no net external torque acting on them, their rotational angular momentum must be conserved. By bringing their arms in closer, they have put more mass closer into their axis of rotation, therefore decreasing their rotational inertia. To maintain angular momentum, the angular velocity therefore must increase. And that's exactly what we've seen happen here. The next question is, what is the change in rotational kinetic energy? So that's going to be really simple. I know that rotational kinetic energy is 1/2 I omega squared. So initially, I'm going to use my initial values. So that's going to be 1/2. His initial rotational inertia was 13, wasn't it? His initial angular velocity was pi. So therefore, his initial rotational kinetic energy is about 64 joules. His final rotational kinetic energy, do we think it's going to go up or down? Well, it's difficult to say. We know that his rotational inertia went down, but his angular velocity went up. And because we're squaring that, I'm probably going to think that that's going to matter more. He's probably increased his rotational kinetic energy. So I can think about it conceptually. Let's see if that is indeed the case. His final angular momentum was 2.6. His final angular velocity was 15.7. And oh yeah, if I square that, I'm definitely going to get a bigger value here, aren't I? 320 joules is the answer. So his change in kinetic energy would just therefore be the difference, final minus initial. So 320 minus 64, 256 joules of energy were added to the system. Where did that energy come from? Nothing interacted with him from the outside, did it? Any thoughts about where this extra energy could have come from? Well, think about what he did. He had to pull those dumbbells in, didn't he? So as he pulls the dumbbells in, it is as if he is doing work on himself rotationally to give him some more rotational kinetic energy. So by pulling the dumbbells in, he spends energy. He spends internal energy in his muscles, ultimately from the food that he ate, right? And it ends up expressing itself as an increase in rotational kinetic energy because, I don't know if you have ever ice skated or been spinning around really quick. You can do it in a spinny chair in your house if you've got one. But it actually takes work. You can feel it. It takes some extra work for you to pull your arms in because pulling your arms in is going to cause you to rotate faster. And that energy has to come from somewhere, right? So the energy that was added here just comes simply from the fact that he pulled his arms in. All right. So the big ideas in this problem, conservation of angular momentum. We know that angular momentum is always conserved. In this case, it was rotational angular momentum because we are treating him as an extended body rotating. So we use this version of the equation, the rotational version. We know it's conserved because there's no net torque acting on him, and that easily allowed us to not only predict what would happen, but to actually calculate what would happen. All right, let's do another example. Okay, so in this example, we have two wheels, wheel A, and this is going to be like a side view. So here's wheel A, and what do I know about wheel A? I know that wheel A has a mass, so the mass of A is 2 kilograms. I know that it has a radius of 0.2 meters. And I know that it's rotating around with an angular velocity of 50 radians per second. And then I have this other wheel, wheel B. So this one is A, this one is B. And I know that the mass of wheel B is 4 kilograms. So it's more massive, but it's smaller in size. Its radius is only 1 meter, 0.1 meter. and it's moving much more quickly here at the beginning. Its rotational velocity is 200 radians per second. And the question says that you basically cause the wheels to collide. Maybe you drop wheel B onto wheel A carefully while both of them are still spinning about, they're spinning about an axis, a central axis, such that after they collide, they start spinning together. I want to know what is going to be their common final angular velocity. What does this remind you of? What types of problems have we done in the past in previous units that this reminds you of? Yeah, this should remind you of an inelastic, a perfectly inelastic collision, right? Remember, with translational systems, an inelastic collision was something like this. We have an object A that's moving this way. We have another object B that's moving, or maybe it's stationary or something like that. We'll say that it's motionless. And then after they collide, what do in a perfectly inelastic collision? Yeah, they stick together, A plus B, and they have some common final velocity, right? So that's exactly what's happening here, just rotationally. So the problem-solving strategy is going to be very similar. We have to recognize that this is a collision. Momentum is really helpful for us to analyze collision problems. This is going to be a conservation of angular momentum question, just like I would use conservation of translational momentum to analyze an inelastic collision like this. And what do you know about energy in inelastic collisions? Energy is not conserved, right? So the kinetic energy of the system should go down. That's what we should predict, and we can actually calculate that. So I know there's, if this is my system, there's no net external torque acting. And if that's true, I can say that the initial angular momentum has got to equal the final angular momentum. What perspective am I going to take? Remember, with angular momentum, we have two different perspectives, translational versus rotational. Well, these are extended bodies that are actually rotating, so I'm going to use the rotational version, right? So remember that rotational angular velocity is I times omega. So it looks like my equation then is going to be this. The rotational inertia of object A times the initial angular velocity of object A, that would give me the angular velocity of wheel A at the beginning, plus IB omega B I, that would give me the initial angular momentum of wheel B at the beginning. This would get me the total angular momentum of my system initially. I know that has got to equal the angular momentum of the system at the end. So the wheels are going to collide. They basically become one object that has one common rotational speed, just like my two carts colliding, or my two objects translationally colliding. If they get stuck together, they have one speed. I treat them as one mass. So remember, before we could just add the masses of those carts together. What can we do here? Well, remember that angular or rotational inertia, these I values, ultimately I just sum them up, right? So this would be initially, finally, wheel A and wheel B are going to be like stacked on top of each other like this. And they're going to be rotating together with some final common angular velocity. The axis of rotation is not changed. The I value for this new system is just going to be the rotational inertia of A plus the rotational inertia of B, okay? That's true because my axis of rotation is not changed. The distribution of mass of B about that axis is the same as it was before. The distribution of the mass of A about that axis is the same as it was before. So the total rotational inertia of the system is just going to be those added together. So I'm going to get IA plus IB. That's going to be my final rotational inertia. And then they're going to have one common final angular speed, just like that. Right? So now all I need to do is, looks like I'm actually going to have to calculate the I values, don't I? Because they were not given to me. So we know that these are basically cylinders or disks, and I hope that you guys remember the equation for the I value of a disk. We've practiced deriving this many times, but the I value of a disk is 1/2 mr squared. So I need to do that for each of these, for IA and for IB. Let me do that real quick. For IA, that's going to be equal to 1/2. The mass of A is 2. The radius of A. And remember that the R value here is, so remember that this I value only works whenever the axis of rotation is through the center of mass. If it's not through the center of mass, I would have to use the parallel axis theorem. So don't forget about that. You have that tool, and that is not on the AP equation sheet, so you do need to memorize the parallel axis theorem. I have videos about that we looked at previously. Because this is rotating, both the wheels are rotating about their center, an axis through their center, then this R is just the radius. I don't need to use the parallel axis theorem. So 1/2 mr squared, that's going to be the value for A. And for A, it looks like that's going to be 0.04. And for B, do the exact same operation. Its mass is 4, its radius is 0.1 squared. It looks like it has a rotational inertia of 0.02. Remember the units for this are kilogram meters squared. All right, so now I think I am good to go to actually start solving this. You guys know that I like to take my equations and rearrange them beforehand. So what am I trying to solve for? Their final common rotational or angular velocity. So very simple. I just divide both sides by this term here, and I'm going to get IA, initial rotational velocity of A, plus IB times the initial rotational velocity of B divided by IA plus IB, just like that. So now I think I can just plug and chug, right? I know that the rotational inertia of A is 0.04. The initial angular velocity of A was 50 radians per second. IB, I just solved that as 0.02. The initial angular velocity of B was 200 rads per second. I do need to make sure I'm in radians per second here. And then I'm just going to add up their rotational inertias to get their the final rotational inertia of the system. And that's just going to be, what, 0.06? Just like that. And when you perform that calculation, you're going to get a final angular momentum of 100 radians per second. Which makes sense. You know, it's going to be somewhere in the middle. This one is going to be sped up, but wheel A is going to be slowed down. So that answer does make sense. Okay, we were also asked to figure out what the kinetic energy was like. We already said that this is an inelastic collision, and we know in perfectly inelastic collisions that kinetic energy is not conserved. So energy must have dissipated out of the system in this collision as heat, as sound, things like that. So I know that the change in kinetic energy, and I am anticipating that there will be a change, is going to be the kinetic energy initial, and I'm looking for rotational kinetic energy, right? Excuse me, final minus initial. And let me build an equation for this. The rotational kinetic energy, as we've seen several times, is 1/2 I omega squared. So finally, it's going to be that common I value, which was IA plus IB, times the final omega that they both share squared. And I'm going to have to subtract away from that the initial rotational inertia of both of them, because remember they were both separate objects, so they're both going to have their own rotational inertia that they had before the collision. So that's going to be 1/2 IA omega a squared initial, the initial rotational velocity that wheel A had, plus that of B, right? And now we can easily plug and chug. So this is the final rotational kinetic energy of the system. This bracketed term here will get me the total initial rotational kinetic energy of the system. And you guys can perform that algebra on your own, but it looks like finally the rotational kinetic energy is 300 joules. And beforehand, all of this, the rotational kinetic energy of A before the collision plus B before the collision, which gets me the total of the system, was 450 joules. So it looks like my my change in rotational kinetic energy, of course, as we expected, went down by 150 joules. Looks like about a third of the initial went away, right? So where does the energy go? Once again, these disks are, when they collide, there are frictional interactions, right? Here they're like grinding together as they rotate. And we know that they're like exerting forces on each other. So each disk independently kind of experiences a net torque, which is going to do work to each of them. Anyway, the most important thing to understand is that energy does dissipate away as heat in this scenario. We lose about a third of the original. Okay, so main concepts in this practice problem. This was a collision. So just like we use momentum and energy to analyze translational collisions, things colliding translationally, we can do the exact same thing for objects that rotate and collide that way. All right. What I would want to do next is see another perspective that we could take for colliding objects that deal with rotation. So let's do another example. Okay, so in this problem we have a door, and I'm going to draw the top view of the door because it's going to be rotating. So here's the door. And let's see, I know that the door has a length, or a width, I guess, of 1 meter. And I know that its mass is 15 kilograms. So this is the top view. And let's say its hinges are here. So here's its axis of rotation, like coming out of me and going down into the page. That's the vertical axis of rotation. So let's say that my kid fires a, oh wow, that's very high powered, a high powered foam dart of mass 10 grams. So here's the dart. And I know that the mass of the dart, we need to be in kilograms. So right away I'm going to convert that to kilograms by dividing by 1,000, so 0.01 kilograms. And it has an initial velocity of 400 meters per second. And it ends up hitting the door exactly in the middle. And it says, the question says that he was firing this exactly perpendicular to the surface of the door. He wasn't firing it, this way or this way. He was firing it exactly perpendicular. So the dart ends up hitting and sticking to the door. Looks like it's going to do that right here. Sticking to the door, and I think that you guys can understand that it's going to transfer some of its momentum to the door, and now the door is going to start swinging this way. So right after this happens, right after the collision, I want to know what is the angular speed of the door. And remember, the door and the foam dart now are rotating together, so I need to keep that in mind. It looks like this is another inelastic collision, doesn't it? So here's kind of the wacky thing, right? The wacky thing is that in this problem, it's a collision problem. What strategy do we have to solve collision problems? Conservation of momentum, right? But don't I have two different types of momentum? Doesn't this dart travel with a translational momentum of p? And then afterwards, doesn't the system have an angular momentum of L? Can these two things like be translated into each other? Can I say that the initial momentum of the system translationally equals the final angular momentum of the system? No, I cannot do that. They cannot be converted into one another. Instead, do you guys know what I'm going to have to do? I'm going to have to view the dart over here as if it has angular momentum to begin with. It is true that it has translational momentum, but remember guys, even if you have a point particle moving in a straight line, we can still say that that point particle has an angular momentum, can't we? It's just that we have to say it has that funky translational angular momentum, which is defined as the cross product of its translational momentum and this r vector, where the r vector is the distance away from the axis of rotation, or the point in space with which we are defining this. And it looks like the axis of rotation, or the point in space that I'm taking my perspective from, is this, the hinges of the door, right? Okay, so I'm going to draw a little diagram over here just to remind you guys of how this works. Here's the hinges, that's the axis of rotation. Here's the dart, let's see, the dart's momentum vector would be pointing this way. That needs to be, I can draw, that needs to be a straight line. And the r vector is always drawn from the axis of rotation to that point. So here's my r vector like this. Yeah. And remember that I'm worried about the angle between them. So what I can do is make basically a right triangle and say that this is the angle between those two vectors, and the cross product is worried about the sine of that angle, isn't it? And I think I've just written this wrong. I think it's r cross p, isn't it? Cross products are not commutative. That does matter, but it's not going to end up changing my answer. That's just a little thing that you guys should think about. Okay, so from this we can see that the sine of this angle is always opposite over hypotenuse, right? So I can say that I hate that it always makes it thick, that the sine of theta is going to be, we could call this leg right here an L or something, so L over R. And if I plug that in here, the R goes away and I just get P, which is momentum, which is going to be mv, the mass of the dart, times the initial velocity of the dart, times L. And remember, this is good news that I've ended up with something like this, because that L is not going to change as the dart approaches. We know that the dart should have the same translational momentum as it approaches. And by recognizing that, taking the cross product gets me the sine of the angle between them. The sine of the angle between the two vectors is L over R, so the R in the equation goes away. So ultimately, the translational angular momentum of my dart with respect to this point just ends up being like the y coordinate, or the height away from that point at all times as the dart travels. And that's exactly what it should be. So there's the initial translational momentum of my system. That is the initial momentum. That's going to be my Li. And again, there's no net external torque. Nothing outside of these two objects is acting on the system. And when there's no net external torque, I know that Li equals Lf, conservation of momentum. All right, so does it matter that initially I have translational momentum of this dart moving relative to this point to get me translational momentum, and at the end I'm going to have clearly rotational momentum of a rigid body? No, it doesn't matter, because they are all angular momentum, and angular momentum, translational and rotational, those can be transferred back and forth. I could just not do this. This is what I cannot do. I can't take just plain old momentum and convert it into angular momentum. I can take translational angular and convert it into rotational angular. That's a fair move in the game. All right. Okay, so I know that my Li then is going to be mass of the dart times Vi times L, where L is, let's just define what L is. I know that the dart hits exactly halfway to the door, so my L is going to be 0.5, right? Okay, so let's think about now what our final angular momentum would be. Well, that is going to be the rotational angular momentum of this rigid body rotating, right? So I know that is I omega, and it is not so simple to and it is not so simple just to treat this I value as the eye of the door. It's going to be the eye of the door plus the eye of the dart, because remember, the dart has stuck right here. Okay, it has been an inelastic collision. They're swinging together, so the total eye of my system at the end is going to be their eye values summed up together. And this omega f, that final angular velocity, that's what I'm looking for, isn't it? So I need to think about now, what is the eye of the door and the eye of the dart? The door is basically a rod. And yeah, it's true that, the door has mass extending down into the page here, because this is just the top view of the door. The door has a height, in other words. But that doesn't matter, because I'm just worried about how the mass is distributed away from the axis of rotation. It doesn't matter if it is a rod or a door, the angular rotational inertia is going to be the same, because they're going to have the same mass distribution relative to this axis of rotation on the hinges over here. So I don't want to take the time to prove this, but the rotational inertia of a rod about one end, so the eye of the door is 1/3 mr squared. Excuse me. It is 1/3 m L squared, where L is the length of the rod. This is the rotational inertia of a rod about an end. You can prove that by finding it about the center and then doing the parallel axis theorem. Why don't we just remind ourselves of that real quick, actually? So here is a rod about its center. Man, we could get into a lot of interesting things here, but I don't want to review this. But an eye of a rod, when its axis of rotation is about the center of mass, is 1/12 ml squared. So to find the eye of the rod about the end, the new I value, when I shift the axis of rotation over to the end, it's going to be, this is the parallel axis theorem, the I about the center of mass plus md squared, where that d is how far over I have shifted the axis of rotation, which is L/2. I've shifted it over from the center to the edge. So that's going to be 1/12 ml squared plus m L/2 squared, 1/12. And I'll let you guys do the algebra, but you do end up getting 1/3 ml squared. So that is for a rod or an extended object like a door rotating about its edge, about its end, which in this case, that's what's happening. So now I need to figure out what the eye of the dart is. And really simple, the dart is just like a point particle, right? Right here, rotating about this axis. So remember that the I value for a point particle rotating about the axis is just mr squared. That's all it is. So the r value is the distance away from the axis of rotation, which is 0.5. So it looks like the eye of the dart is going to be 0.5, or excuse me, it's going to be the mass of the dart times what I'm calling L squared, where L is the distance away that the dart is from the edge of the door, 0.5 meters. Okay, so let me clean up my big mess here so I have room. So now that I've done all of that, I can say major concept here is that Li has to equal Lf, where Li is the translational angular momentum of the dart flying, and I found that right here. So mass of the dart, initial velocity times L. And yes, it is the same L that ended up in this expression here. And that's going to equal the final angular momentum of my system, which is going to be the eye of the door, which is 1/3 m. And the length of the door, let me call that capital L, is 1 meter. I'm going to plug all my variables in later. Plus the eye of the dart, which is the mass of the dart, times L squared. That gets me the final rotational inertia of the system times that angular velocity, omega f. Omega f is what I'm trying to solve for, so I rearrange the equation. I get omega f equals the mass of the dart times the initial velocity of the dart times little l over 1/3 m big L squared plus the mass of the dart times little l squared. This big M here is the mass of the door. I just realized that earlier I called it M door. Why don't we make it big M so we don't get confused? And now you guys can just plug and chug these values, right? So once again, the main idea here is that angular momentum is conserved. And it doesn't matter that the dart has translational angular momentum at the beginning and the whole system has rotational angular momentum at the end. Angular momentum is angular momentum, so I can make this equal. I know angular momentum is conserved because there's no net external forces acting at all. So this is my final equation, and I will let you all plug that in and solve. But you should end up getting 0.40 radians per second. Okay. Now let's see what has happened to kinetic energy. So change in kinetic energy is going to be kinetic energy final minus kinetic energy initial. And this time energy is energy. So my final energy that I have is rotational. But the initial kinetic energy I have is just plain old kinetic energy of the dart flying, right? Well, kinetic energy is kinetic energy. Unlike momentum, where I could not say this is not the conservation of momentum that I can use. I cannot go from translational momentum to angular momentum. Unlike that, energy is energy. So it doesn't matter at all that this is technically like a translational kinetic energy that the dart has at the beginning, and that this is a rotational energy that the system has at the end. That does not matter at all. I can combine them into one expression. So rotational kinetic energy is going to be 1/2 the eye of the system at the end, where remember the dart is stuck to the door, so the eye of the door plus the eye of the dart relative to the axis of rotation, 1/2 I omega squared. That's the omega f that I solved for earlier, right? Their final common rotational velocity. Minus 1/2 the initial kinetic energy is just coming from the flying dart, so 1/2 mass of the dart times vi of the dart squared, that velocity squared. So you guys can plug and chug that. You end up getting that the final kinetic energy is, it's really small. It's only 0.40 joules, where the initial was really big, 800 joules. So we lost a lot of energy. This is like a violent, I mean, it makes sense. This dart was flying, right? It was going very quickly, and all of a sudden it gets stopped by this door. We're going to lose a lot of energy in this collision to heat and sound, frictional interactions, things like that. So what is that going to be? Yeah, we've lost the majority of our energy, haven't we? We've lost like uh, almost all of it. So the big idea here that I wanted to go over this problem with you about is angular momentum is angular momentum. So even though this dart is moving in a line and it does technically have regular old-fashioned momentum, we cannot use that. We have to turn it into a translational angular momentum by defining this motion, this momentum that the dart has relative to this axis of rotation by doing this cross product thing. So you guys really need to make sure that you understand this. This is probably what trips a lot of people up. So you need to make sure that you understand this equation and how it works. Okay, and why it ends up just being this with that L value, no matter where the dart is, that's always going to be true that the sine of the angle between them is L over R, where the L is this leg of this right triangle. Here's my R vector, and so that ends up canceling out. So in questions like this, you do need to be able to collapse it down into something like that. We've done that in a video previously. And then the final angular momentum of the system is a rotational angular momentum, which is I omega. And we had to recognize that the door and the dart are stuck together. They both are going to have an I value about this axis. Okay, so conservation of angular momentum. And then unlike momentum, kinetic energy is kinetic energy. So we can combine rotational and translational kinetic energies into one term because energy is energy. All right, and this was an inelastic collision where the two things become one object, just like last time. So hopefully you guys understand that. If you have any questions at all, feel free to email me, reach out to me, ask them in our next class. We do have one more example problem I want to work through, so we will do that next.